Dear students, I myself is Gunakar De. I want to teach you through YouTube the class 10 mathematics. I have a constant touch with mathematics for the last 30 years. I have completed my MPhil degree in mathematics. So I think to teach especially the class 10 students, which will be beneficial for their board examination. I will not teach the theories or the problems. I will enhance your thinking power by which you can guess a question and imagine yourself and enhance your thinking power how to solve a problem. Let us now study the real numbers, Chapter 1 of CBSE course of class 10 mathematics. I have already noted the problems and the theories in a paper or in a khata, and I will read in details. You will, wherever it is necessary, I will give you some instruction or elaboration. Now I am going to read in details which will be beneficial to you. In earlier classes, we have read about natural, whole, integers and rational numbers, which are generally denoted as follows. Natural number 1, 2, 3 up to infinity denoted as n. Whole numbers 0 including the natural number denoted as w. Integers minus infinity to 0 and 0 to infinity, that is denoted as I. And the rationals in the form of p by q, where p and q belongs to I and q is not equal to 0. This aspect is a major thing. Always whenever we are going to divide in p by q, we are dividing q. When q, anything is divided in mathematics, it should not be 0. The denominator should not be 0. So it is denoted as q. But the set of real numbers is not yet completed. Besides rationals, there exists a number system called set of irrational numbers, which is neither of the above number system n, w, I or q. We denote it as q dash. The set of rational and the set of irrational numbers as a whole represents the set of real numbers and denoted as r. Towards the end part of this chapter, we will read about the nature and property of irrational numbers. So n, if we denote is n, it is whole number, it is w, it is q. So q includes in it the n, w, and w, I, and w and I. Means a number n belongs to n or belongs to w or belongs to I is automatically belongs to q. Suppose 5, we can denote it as 5 by 1, i.e. in the form of p by q, q is equal to 1 not equal to 0, belongs to q. 0 is equal to 0 by any number belongs to q. Minus 5 is equal to minus 5 by 1, that is equal to p by 5 by, that is equal to p by q form, belongs to q. But the converse is not true. A number belongs to q say 2 by 3 is may not be a natural or W or I. Now let us now study a very important theorem of mathematics, that is known as fundamental theorem of arithmetic. Every composite number can be expressed as factorial. Every composite number can be expressed or factorized as a product of primes, and the factorization is unique irrespective of order. Explanation of this. How I will explain this theorem? That there is a difference between prime factors and only factors. A number can have both prime and composite factors like 24. 24 has factors 1, 2, 3, 4, 6, 8, 12, 24, out of which only 2 and 3 are prime factors, and the others are composite factors except 1 and 24. We can express 4, 6, 8, 12 as a product of only 2, only 3 or both. So the only prime factors of 24 are 2 and 3. We can express 24 is equal to 2 into 2 into 2 into 3, that is equal to 2 to the power 3 into 3. Only prime factors are 2 and 3. We can express 24 as, if you change the order, 2 to 2 into 3, it is 2 into 3 into 2 into 2, 2 into 2 into 3 into 3, irrespective order. So order does not matter. Like composite number, prime numbers, only factors are 1 and the number itself, like 13, that is equal to 1 into 13. But a composite number has more than 2 factors, which are 1 and itself, like 6. It has 1 and 6 factors, which is obvious, obvious. Besides this, other 2 factors are 2 and 3, which are also primes. Basing on this unit factorization method, i.e. fundamental theorem of arithmetic, we can solve the following problems, from which the intrinsic meaning of the theorem will be more clear. Question: for any natural number n, prove that 4 to the power n does not end with 0. Here a number and a digit, there are certain difference in it. Between these two, digit we have only 10 digits. Those are 0, 1, 2, 3, 9. These numbers, these digits are also number, and these are called one digital number. But 15 is a two digital number with digits 1 and 5. Moreover, the end digits represents always the unit place or unit place digit, which we can also call as the end digit, which is told in this question. Does not ends with 0 means the unit place digit of the number 4 to the power n can never be 0. Now we have proved this according to the fundamental theorem. How to prove this? Prior to go ahead on proving first, we shall check few numbers for our convenience. 4 to the power 1 is equal to 4, 4 to the power 2 is equal to 16, 4 to the power 3 is equal to 64, 4 to the power 4 is equal to 256, 4 to the power 5 is equal to 1024. The unit place is always 4 or 6. Moreover, never 0. Moreover, never 0. We have to generalize the proof. The above examples are only particular cases where we have taken n is equal to 1, 2, 3, 4, 5 only to understand the fact. Actual proof. The unique factorization of 4 is 2 into 2, i.e. 2 is the only prime factor of 4. Now 4 to the power n is equal to 2 into 2 whole to the power n, that is equal to 2 to the power n into 2 to the power n. That is by the process of 2 to the power 2n, use a to the power x into a to the power x is equal to a to the power 2x. Let unit place to be 0 means the number must have prime factors 2 and 5, otherwise unit place cannot be 0. So 4 to the power should have prime factors 2 and 5. But above we found that 4 to the power n is equal to 2 to the power n only prime factor 2. But fundamental theorem of arithmetic says the prime factors must be unique. It is the most fundamental thing, unique. Once it will, suppose once it will be like 2 into 2 into 2, again it will never be like 2 into 5, all these things. So simultaneously prime factors 2 and 5 cannot occur, implies our state assumption unit place digit to be 0 is wrong. So 4 to the power n cannot have a unit place digit 0. In mathematics, very often we prove an aspect by contradiction method. We assume something, finally arrive at a contradiction which proves that our assumption is wrong. In this case, our assumption 4 to the power ends with digit 0 is taken as leads to 4 to the power has two sets of factorization 2 into 2 into 2 into and 2 into 5, which is wrong. So 4 to the power n number has end points 0. Now we will read the HCF, highest common factor, and LCM, lowest common multiple. These are two differences. One is multiple, the other one is the factor. Factor is the highest and the multiple is the lowest. From this fundamental theorem of arithmetic, we will conclude that HCF of two or more numbers, that is called the product of the smallest powers of each distinct common prime factors in the, it is the distinct common prime factor in the number. LCM of two or more numbers is equal to the product of the greatest power of each prime factor. Each prime factor occurred in the number. For example, take two numbers 96, 404. By fundamental theorem of arithmetic, 96 can be expressed 2 to the power 5 into 3, which is unique. Which is unique. 4 to 4 can be expressed as this, which is unique. For HCF of both numbers, we have to consider first the common prime factors, which is 2 to the power 5 and 2 to the power 2, and the smallest power of the two is 2 to the power 4 is equal to 4 is the HCF. 2 to the power 5, 2 to the power, the lowest is 2 to the power 2. And in 3 and 1 0 there is no common. For LCM, we have to consider the individual factors, i.e. 2 to the power 5, 3, 2 to the power 2, 1 0 1. And out of this, the greatest powers of 2 to the power 2 to the power 2 is 2 to the power 5, and the other factors 3, 1 0 1. So LCM is 2 to the power 5 into 3 into 1 0 1, that is 96 96. 3 and 100 has no other power factor. So we have taken the lowest 1, 3 to the power 1, that is the lowest. 1 0 1, that is also the lowest. Here important thing is that the HCF, highest common factor. Highest common factor. If we take 4 and 12, 1 is also a factor, 2 is also a factor, 4 is also a factor, So meaning of highest common factor is out of 1, 2, 4. 4 is the HCF, which is also proved from the fundamental theorem of arithmetic, as 4 is equal to 2 into 2, that is equal to 2 square. 12 is equal to 2 into 2 into 3, that is equal to 2 square into 3. So the common highest lowest factor is 2, that is equal to 4. But in case of LCM, we use the word lowest. For example, For example, 8 and 20. 8 has factor 2 into 2 into 2, that is equal to 2u. 20 has factor 2 into 2 into 2 square into 5. If we take 2q into 5, 2q will be the LCM as 2 to the power 2, highest is 2 to the power q, and 5 to the power 1, highest is 5 to the power 5. But the meaning is if we take 2q into 5, that is equal to 8, 5, 40, 48 divides 40, also 20 divides 40. No other number less than 40 will divide 8 and 20 simultaneously. So the word minimum or least word is used here. 8 and 20 also divides any multiple of 40, i.e. 40 into 2, 40 into 3, so on. But out of these, only 40 into 1 is the least. So the word meaning of least is satisfied here. Now there is a very basic formula or very important formula regarding LCM, HCF and the two numbers is that LCM into HCF is equal to product of two numbers. For example, a question like find HCF and LCM of 12, 15 and 21. Solution: 12 we can factorize 2 into 2 into 3 or 2 square into 3, 15 is 3 into 5, 21 is 3 into 7. HCF must be the common factor with smallest power. Since in three numbers 3 to the power 1 is the only common factor, implies 3 is the HCF. For LCM, the highest power of all possible different prime factors, which is 2 square, 3 to the power 1, 5 to the power 1, 7 to the power 1 is equal to 420. So, this is the difference between HCF and LCM. And now we will establish the formula, that is LCM into HCF. HCM into LCF is equal to product of two numbers. Suppose 15 and 25 are two numbers. Their HCF is equal to 5, LCM is equal to 175. Now HCF into LCM is equal to 5 into 75, 7. Product of two numbers, 15 and 25. पंद्रह पचास पचास पाँच 375. Same proved. That's HCF into LCM is equal to product of two numbers. Another question: 6 to the power can has a and digit, has a digit 0, has a and digit, digit 6 to the power can has an and digit 0. Likely in the previous case we have read 4 to the power n has no endpoint 0. Likely in the same way we will prove this. Solution: let us now factorize. Prime factorization 6 is 2 into 3 to the power n. This is equal to 2 to the power n into 3 to the power n. This implies the only prime factors are 2 and 3. No other factor is there. It is true, it is 3. And some power. Power is, it will not change the, it may change the factors, but it will not change the prime factors. Now, what is factors and prime factor? Factors and prime factors has some difference. In 12, the prime factors are 2, 3, 2 and 3, but it has factors 2, 3, 4, 6, out of which 4 and 6 are not primes. They are the product of 2 into 2 and 2 into 3. So, there may be so many factors, but prime factors may be few. Like in 8, prime factors are only 2, but factors are 2 and 4. So, we have prime factors 2 and 5. But as per FT fundamental theorem arithmetic, prime factors of 6 to the power n must be unique, i.e. must be 2 and 3. Since 5 is not there, so 6 to the power n can never has a n digit 0, because to have an end digit 0 besides factor 2, there must be another prime factor 5. Since 5 is not there in the factor of 6 to the power n, so we will never get a digit which ends with 0. So that this 7 into 11 plus 13 into 13 plus 13 is composite number. We need not multiply all the 3 numbers and then add with 13. Shortcut way is there. Just take common as in case of following: a into b into c plus c is equal to c into a into b plus 1. Similarly, 7 into 11 into 13, we can take 13 as common. That will 13. Out of this, it will be 7 into 11. This will be 1. That will be 13 into 78, which is clearly a composite number because it is the product of 2 numbers. It may be composite or prime, does not matter. Since product of 2 numbers means it is always a composite number. In the above question, instead of 13, if 7 or 11 is added, we get a composite number by the above process. But we cannot say at a glance if some other number is added or subtracted except 7, 11 and 13. We have to calculate it in detail. For instance, 7 into 10 plus 10 is equal to 77 plus 10 is equal to 87, composite. 7 into 11 plus 6, 77 plus 6, prime. As the number added is neither one of 7 and 11. Similarly, question 1 into 2 into 3 into 4 into 5 into 6 into 7 plus 5, a composite number, a prime number. Clearly, as before, we can take, it need not multiply in detail, just take common 5 because 5 is there. Here it is 5, here it is 5. It is added, it is multiplied. So if you take 5 common, every multiplication will be there except this 5. And 5 is taken to outside, it is multiplied 5 into 6 plus 1. So whatever the number it is a say number. It is a particular number. The product will finally arrive a number plus 1. It will be another number. So 5 into a means a composite number. Total we can say as a. 5 into a. It is a composite because it is the product of 5 and another number. Now let us study about the irrational numbers. A number which cannot be expressed in the form of a rational i p by q, where p, q belongs to I and q is not equal to 0. For example, root 2, root 3, 2 plus root 3 pi, 0, 0.10, 110, 110, 410, all and up to infinity. All these numbers are irrational numbers. We cannot express as a form of p by q. To prove root 2 is an irrational number, we wrote that any root of a prime number, root over of p, where p is a prime number, is always an irrational number. Like root 2, root 3, root 5, root 7, root 11, root 13, these things. Proof. Here the main criteria is p must be a prime number. To prove root 2 is irrational number, prior to prove this, we have to prove another theorem. Like if p is a prime number which divides a square, then p also divides a, where a is a positive integer. Here the main criteria is p must be a prime number. This is the most important thing. P must be a prime number. Otherwise the theorem is not justified. For example, if p is equal to 0, prime divides 6 square is equal to 36. This implies p is equal to 2 also divides 6. Okay. But p is equal to 4, not prime, divides 6 square, that is equal to 36. Does not imply that p is equal to 4 also divides 6, which is wrong. So the main focus is p must be a prime number. Let a is equal to, a is a composite number, it has some factors. These factors are all prime factors. All pi are prime numbers, necessarily all distinct, not necessarily all distinct, because we have written this p1, p2, p3, we can express 2 into 2 into 2, all these things, and into 3, so it need not be all distinct. p1 may be equal to p2, p2 may be equal to p3, p5, p7, p8 may be equal to one product, one factor, it does not matter, but this should be all prime factors. Implies a square is equal to, we just will multiply p1 square, p2 square, p3 square into pn square, because if you will multiply p is equal to x into y, implies p square is equal to x y whole square, that is equal to x square into y square, that is equal to p1 square, p2 square. In this case it is written, so p1 square implies p1, p2, p3, pn are also factors of a square. If their square is a factor, then p1, p2, p3 are also factors of a square. So a square has a factor p1, p2, p3 and a pn. Like if m is equal to xy, this implies m square is equal to x square y square. This implies x square is a factor of m square, implies x is also a factor of m. Since given that p divides a square, it is that p divides a square. P divides a square means p is a prime factor of a square. Implies p is one factor out of p1, p2, p3, because by the fundamental theorem we know that p is one factor out of p1, p2, p3, pn. 2 divides 2 into 3 square, 2 square, 3 square, 2 into 2, 3 into 3, implies p divides 2. If p square divides, p divides 2. But a is taken p1, p2, p3 into p4 dash up to pn. Implies pi is a factor of a and p is also a factor of a. Proved above. Thus, by fundamental theorem arithmetic, p must be equal to any one of pi, p1 to n, implies p divides a. Proved. If p is other than any pi, it will violate the fundamental theorem of mathematics because the factorization is unique. Now, we will proof of root 2 is an irrational number, which is very often asked in the board examination. Root 2, root 3, 2 plus root 3, 7 root 3, all this, like all these things. So, we will prove this by the method of contradiction I have told you earlier. Let us assume that root 2 is a irrational number in the form of p by q in its lowest form, where p, q in the lowest form can also be otherwise taken as p and q co-primes, means that they have no common factor other than 1. We cannot take p by q as 4 by 6, as 4 by 6 is neither co-prime nor in lowest form. The actual p by q will be 2 by 3, which satisfies they have only common factor 1. So this is the lowest form or co-primes, whatever it may be taken. So root 2 is equal to p by 2 implies root 2p by cross multiplication. P implies squaring both sides, so we will get 2q square is equal to p square, implies p square is equal to p square, just to change the side, p square is 2q square, implies 2q square is always has factor 2, implies 2 divides p square, implies 2 also divides p by the above, by the previous formula, by the previous theorem, as 2 is prime. If 2 divides p, we can express p as 2 into m for some mi. P divides p means 2 divides p. 2 divides p means p is equal to 2m for some m. For some m belongs to I, implies p square is equal to 4m square. If p is equal to 2m, p square is equal to 4m square, implies that 2q square is equal to 4, because 2q square, p square is equal to 2q square. P square is equal to 2q square, p square is 2q square, 2q square is equal to 4m square, implies q square is equal to 2 square. This implies even. This implies 2 divides q square. This implies 2 divides q by the above theorem. So, says q is equal to 2 into n for some n belongs to I. It is p is equal to 2 into m for some m belongs to I. Q is equal to 2 into n for some n belongs to I. Finally, we get that p is equal to 2m and q is equal to 2n. P is equal to 2m, q is equal to 2n. Which says that they have given a common factor. They have again a common factor 2. If it is 2m, it is 2n. Then p by q is equal to 2 by m is equal to 2 by n, which is not in its lowest form because 2 is common in both, neither co-prime nor in lowest form. It has again a common factor 2, but we have taken that there is only a common factor 1, which says that they have given a common factor 2, but this contradicts that p and q have no common factor other than 1. This contradiction was due to our wrong assumption that root 2 is rational. So the actual conclusion is root 2 is an irrational number. Note: Q is equal to set of all rationals, obviously include all natural, whole, integer in it. Set of irrational number is a separate branch of number system. A number be either rational or irrational, but not both. as proved above, because a number is root 2. Root 2 is an irrational number. It cannot be a rational one. A set of real numbers in IR is the combination of set of all rationals and Q and set of all irrational Q dash. Co-primes. Just to elaborate or give a clear concept, let A and B are co-primes where their HCF is 1. Like 5 and 7, both are primes. 5 and 8, one is prime, other is composite. 4 and 15, both are composite. So, for co-primes, it does not mean that the numbers must be prime. Only their common factors must be 1. So, the numbers may be both primes, prime and composite combined, or totally both numbers are composite. Then we can call it co-primes. Now, we come to this is a note. This is very important. You should remember in your mind, and you should go all these things, whatever written, you should go in details. Then you can memorize it. First, rational plus minus irrational. Plus minus means you can add minus is also a plus. Minus is also a plus. Means we add the negative. 2 plus minus 3, that is equal to 2 minus 3. Always irrational. Whatever the numbers may be, rational or irrational, when we will add rational plus irrational, always irrational. 2 by 3 plus minus 3, for example. In any way, it will always an irrational number. Irrational, irrational. We cannot say it is always rational or always irrational. Basing on the numbers, it may be rational, it may be irrational. Suppose you take in this way, the rational 0 by q, q is not equal to 0, it is equal to 0, 0 is rational. But this one, 8 root 3 or 2 root 3 irrational. So irrational plus minus irrational. So when we will add or subtract two irrationals, the resultant may be rational or irrational. So the rational into irrational, it is always irrational, like 2 into root 3. Any irrational, if multiplied with another rational number, the resultant is always irrational. But if you multiply two irrational numbers, the result may be rational or may be irrational, like this. 2 into minus 2, it is an irrational number, it is an irrational number. They are not same, they are different, but their product is minus 2, which is rational. And these are two irrational numbers, all are different, their product is an irrational number. Similarly, rational division irrational, always irrational. In whatever way you divide, it is always an irrational number. But irrational divide irrational, may be rational or may be irrational. The examples are clear here. So, whereas for any two rational numbers a and b, a plus minus b, a into b, a division b, provided b is not equal to 0, is always a rational number. So, is always a rational number. Only in case of irrational a and b, for any two rational number a and b, a plus always a rational number. Note, root over of any prime number is always an irrational number, root p is always irrational number. Whereas for any two rational numbers a and b, in which way, either you plus it, minus it, multiply it, divide it, rational number always gives a rational number. But in case of rational and irrational, it will combine both. Their summation, their subtraction, their multiplication, their division will give different values basing on the numbers.